Hi everyone. Gonna get started with the stream now. Um, so Codeforces is a little slow, but it seems like it's working fine. It's up, but it's slow. Cool, yeah. So I opened all the problems over here. Hopefully that'll uh not go away during the stream. Um, yeah, and is the stream and the stream audio and video is fine for now, right? Just wanted to double check that before I get started. Okay, great. Um, cool. So thanks everyone for joining. So today I participated in this Codeforces Division 3 round and solved all the problems. So I'll just be going over the solutions on the stream. I'm going to try to go through how you would think about how to solve each problem, what the solution is, and then go through the code quickly. Cool. So let me just let me set up commands. Cool. All right, so let's get started. Actually, I'll wait just a minute because it seems like a lot of people are still joining. Um, and then I'll get started. Apparently I beat someone by 3 leaderboard places. Let's see. I was on the second page. Nice. Well, pretty cool. Um, right. Cool. And I got my first hydrate of the stream. Okay, great. So let's get started with A. Um, Someone said, "How is my name spelled?" It's just spelled the same as on Twitch and on Codeforces. Um, oh, for me, the math on Codeforces like doesn't work. Does anyone know how to fix this? Um, it's super annoying actually. I don't know what would be causing it. Anyway, I guess we can just do this um without being able to see the math properly. Yeah, so it works fine for me and my other computer, but not on this computer, which is the one that I use for streaming. So it's a little weird. So I did the contest on another computer where the math was fine and it wasn't too annoying. But anyway, let's just get started with this. Definitely encourage everyone to open the problems on their own computer if they want to be able to read them more nicely. Um, Actually, maybe I can just use another browser. Do I have Firefox? Do I have Edge? That's super weird. It actually doesn't even work for me in Edge. So like using a completely separate browser. Um, anyway, let's get started. We don't need that, I guess, for now. So for A, basically what they're saying is you can always cut the sheet of paper in half. And if you cut the piece of paper in half, then it makes both of the remaining pieces identical. So then whatever you do with one of them, you could do with the other. That's kind of the key insight. So if you have this paper and you cut it in half, and then you somehow divide this one into four pieces, then you could have also done the same thing dividing this one into four pieces. So basically what we want to do here is we want to figure out how many times we can divide it in half uh, vertically, and then how many times we can divide it in half horizontally. And then if you multiply those, you kind of get how many final pieces you can divide it into. Um, so let's look at the code. So the code here is pretty simple. You just read the width and the height, and then once um, you just count how many times you can divide it vertically, and then multiply the maximum number of pieces you can get by 2, and then you count how many times you can divide it horizontally, and then multiply these by 2, and then if you can get at least n, then you end up printing yes. All right, let me catch up with chat. What was the h times w over 2 thing? No, I think you do need both, right? The idea is you can cut it horizontally or vertically, not just both. So that's important to see. Um, and then some other people are saying some stuff. Someone asked if it would be an infinite loop. The answer is no, because um, we stop once the number wait, hold on. Oh yeah, so actually, yeah, so what happens is you'll always have an integer, and then eventually you'll reach an odd number, at which point the loop will terminate. And you can do this using bitwise operations too, but since it's problem A, you want to make sure you really get it right. So I just coded it kind of the simplest, least thoughtful way I could think of. Okay, cool. So let's move on to B. Oh. Okay, great. It looks like the problems are more clearly readable using Microsoft Edge. So let's do that, and let me just open all the problems here. Okay. So oh yeah, and then people are asking if this will be uploaded to YouTube. So you can join my Discord, and you can also check out my YouTube. And I do upload all my streams to YouTube. And there are a few very kind volunteers on my Discord who timestamp the videos. Why is there a anyway? Okay, so at least those look okay. So only the current problem I'm working on will have a math processing error. Okay. So anyway, let's just go over the solution to B. And yeah, as I mentioned before, definitely if you have trouble reading the problem, just open it on your own computer or on your phone or something. And this is the link to the problems. Okay. So for B, they basically received a bunch of candies and they either weigh 1 gram or 2 grams. For this one, actually, I think it's useful to just read the code. So basically, if the total sum is odd, you definitely can't divide it evenly in half. So definitely keep that in mind. So if that's the case, you just immediately return false. Then, if the sum is even, it turns out that it's also possible that you wouldn't be able to divide it evenly if the sum is even and all of the candies are size 2. An example being if you had 3 candies of size 2, um, you wouldn't be able to get 3 and 3 because you could only get like 2 and 4. So that's what we check here. And then in all other cases, the answer is true. And the reason for this is that if you have any ones at all and the sum is even, it means that you have 2 ones, which means that you can either combine the ones into 2s and just split everything as a bunch of 2s, or you can put 1 into each bucket and then split the rest of the stuff as 2s. Cool. All right, so let's check out C. Oh, and please don't post like entire like long blocks of code into chat. Like yeah, and honestly, you probably shouldn't ask for debugging help in the chat anyway because people probably won't really be able to coherently describe it. Um, by the way, if you want to see something that was earlier, you can always rewind in the current video. And some people are asking about Java. So the Java implementation would basically be the same. You can, if you're familiar with either C++ or Java, you should be able to read the other one. Cool. So let's read about this game. Okay, so let's go through an example. So they had the example 7, 3, 1, 2, 3. So the idea is if you pick any starting point, what you do is you go that many squares to the right, and then you continue playing. So from here, you would go to here, and then from here, you would leave. And like from here, you would go to here, and then I guess you would leave. So the important thing to note is that because you can always only go to the right and you can never go back to the left, then what this means is if we find the optimal answer starting from, let's say, here, and then there's another thing that points to it over here, then this answer will just be this answer. Well, I'm saying optimal answer, but it's really the only answer. This answer will be this answer plus whatever the weight of the edge between them was. So if you just process everything in the right order, then you're able to solve this cleanly in linear time. So in this code, this is the answer starting from I. So starting from the wherever you're starting, if your jump would take you out of the array, then you're kind of done playing, and the answer is just AI. And if your jump takes you to another thing, then it's all the stuff you would get starting from there, plus the AI that you just added. And then once you do that, you have to make sure you take the max of all of those to figure out what the actual best starting point is. So, for example, if we look at what happens if you actually run this, for this example, it's actually best to start from the second square instead of the first one. But since we take the max, that ends up covering that. Cool. All right. Some people are asking some other questions. Someone asked, what does Clang format do? Basically, I have my thing set up to auto format whenever I save my file. But I don't want to auto format my template because it's kind of hand formatted to take up a bit less space just because it's the same every time. So everything between Clang format off and Clang format on doesn't get auto formatted. And then the code that I'm actually writing, I want it to get auto-formatted to make sure it's easy for me to read and understand while I'm coding. Someone's asking about my Vim dot files. I think they probably won't be that useful. It's probably best to figure out your own kind of what Vim dot files you want to use. And just as a quick reminder, you can always join my Discord, and hopefully that'll expand and become a little more interesting. Right now, I'm basically just using it to announce what my future stream plans are. Okay, so let's do D. Actually, I thought D was a super, super cool problem. So let's think about the possible cases. We'll type these up. Whoa. Okay. If Alice picks... So the key observation here is that these people are playing like a zero-sum game. Like, Alice wants her score to be high, but she also wants Bob's score to be low. Apparently a lot of problem Ds got hacked, so hopefully mine doesn't get hacked. Actually, that'd be kind of cool if mine got hacked while I was streaming. So yeah, definitely encourage people to hack my solution. And let me know in the chat if you did, because then I can fix my bug before it goes in the YouTube video. Okay, so we want to consider the score to be Alice's score minus Bob's score. So then Alice wants to maximize, Bob wants to minimize. Alice wins if score is positive, Bob wins if score is negative. And this is exactly equivalent to the original cool, I gotta hydrate. This is exactly equivalent to the original problem, right? If A minus B is positive, that means A is greater than B. Okay. So now let's look at what actually affects the score. So if Alice picks an even number, then you add to the score. Alice picks an odd number, nothing happens. Bob picks an even number, nothing happens. Bob picks odd number, score gets minus equal x, right? Where x is the number that you're picking. So we can kind of do this cool trick where first we assume, and so we can actually just look at what Alice chooses, and then Bob chooses everything else. So first we assume Bob chooses everything. Then score is the sum of all odd numbers. And now, for every number Alice chooses and takes away from Bob, we do score plus equals x. So the reason for this is we can just do a little casework. So first, if Bob gets to choose everything, then the score is actually, it's going to be the negative sum of all the odd numbers. Because for all the even numbers that Bob chooses, nothing happens, and for all the odd numbers that Bob chooses, the score gets subtracted of those. Oh, someone said they're sad because they couldn't solve A. But yeah, definitely hoping you can solve it next time. Yeah, other people are encouraging you. That's awesome to see. So anyway, so if we assume Bob chooses everything, this would be the original score. And then the cool thing is now odd and even numbers are treated the same. Because for every number Alice chooses, if it's an even number, Bob's score doesn't change, but Alice's score increases. And if it's an odd number, Alice's score doesn't change, but Bob's score decreases. Like you take that away from Bob. So if we think about it this way, I'll show the code. So also note here that I used longs 32-bit, or sorry, 64-bit integers. because if you look at the constraints, even though all the things fit into a 32-bit, the sums could overflow. So you have to be careful of that. So someone's asking about a greedy solution. So this is a greedy solution. So I'll explain via the code. So the initial score is the negative sum of all the odd numbers. So we can see here we're just finding the odd numbers and subtracting them from the score because Bob picked them. Then what we're doing is we sorted our array in reverse. So we're going to pick the largest numbers first. Because for every number Alice chooses, this cool aggregated score differential increases by that amount. So Alice just wants to pick the biggest numbers regardless of whether they're even or odd. So Alice will end up getting to choose every other number. Bob wants to block Alice from choosing numbers as well, and Bob wants to pick the largest number at each step. So we go through the first number, the third number, the fifth number, and so on, and Alice chooses all of those, and those increase the score. This is after we've sorted it so that we're picking the largest things first. And then we just have this if statement, right? If Alice's score is higher, then you print Alice. If Bob's score is higher, you print Bob. Otherwise, you print tie. Yeah, some people are saying they changed to long, long, and then it passed. So yeah, definitely be careful with definitely be careful with that. um, let's see what else. Someone's asking what's R all. It's basically just taking the reverse iterators for A. So when you sort it ascending in reverse, you end up sorting it descending. Let's see. Yeah, some people are asking why Alice would choose certain stuff, and basically the thing is with this cool transformation we did, we don't end up caring about whether stuff is even or odd once we get to the main phase of the game. So we can just sort everything by how much value it adds to the score. Cool. Yeah, and for people saying that they can I explain stuff again that I've already explained? I won't do that just because I don't want the stream to take forever and repeat myself for the other people watching. But you can always do the !rewind command to see how to go back in the current video. And you can always watch the stream later on YouTube. Cool. So let's look at E. I think I already have it open. Okay, so E was definitely a pretty tricky one. And some people are asking why I'm streaming on Twitch instead of YouTube. I mean, I had to pick one, and I like Twitch. It seems like Twitch is like my feeling when I started out is that Twitch is like kind of stream first, and YouTube is like video first. So I figured I'd stream on Twitch and then upload to YouTube later. Cool. All right, so let's do E. Some people are saying E destroyed me. Yeah, E was definitely a tough one. And it took me a while to debug my solution when I was coding it up. All right, so let's explain E. So they kind of explained this complicated looking constraint, but basically the idea is you can either have a rectangle like this, or you can rotate it 90 degrees to get a rectangle like this. And then you want to fit a rectangle that's smaller than it in both directions. And you want to see if one exists, and if it does exist, you wanna find it and like print it out. So the kind of cool trick here is for kind of our word bank, or like our list of available rectangles, what we can do is we can actually take every rectangle and we can take the transpose of every rectangle and we can add all of those in. The only potential problem would be if you wanted to use like instead of like putting somebody else standing in front of me, you wanted to have like me lying down in front of me standing. But you would never actually have that problem because if you transpose a rectangle, it's impossible for both dimensions to become smaller. Um, and like someone else said, they sorted by area, which I think may have also worked. Um, so the cool thing that you can do here is I actually visualized all the rectangles as points. So I just put their lower left corner at the origin, and then each rectangle becomes like some point here. And then you also want to draw all their transposes. Um, this is kind of a funny diagram. Anyway, so once you draw their transposes, if you sort the points by x coordinate, you can kind of sweep through, and you can keep track of for let's say we're looking at this point, we want to find something that's down and to the left of it, which means that it's something that we've already passed if we're doing like a horizontal sweep through the points like this. So what we want to do here is we want to consider as we're sweeping through, what's the best candidate point we've seen so far? And the best candidate point you see so far would be so first of all, the x coordinate of the points you've seen so far doesn't matter because we know that all of them will be less than the current point. And there's a little bit of subtlety here where you could have duplicate x coordinates, which is actually the source of my debugging. But we'll solve it this way for now, and then we'll deal with the duplicates issue. So the best candidate point so far, the x coordinate doesn't matter, so we just want to pick the one with the lowest y coordinate because that makes it the most likely to be helpful. Um, because we want to, if something, if like two different points both worked, then the smaller one like will always also work, if that makes sense. Um, cool. So let's look at the code now that we've kind of explained the idea a little bit. And my code is a little bit it's a little long, but I just did it the most straightforward way I could think of. Someone says I'm explaining really well. I definitely appreciate that. That's always great to hear. I guess before I look at the code, let me catch up on chat a little bit. Okay, awesome. So here I just have a pre-written point class, which is just like for convenience, but you can just use pairs or like anything else. So we read in the original list of points. Then what we do is we create a new list of points, which contains... Oh, actually, there is one more cool thing that I'll point out. So here, if we find a point that's less than that maps to another point, um, if our second point, the larger one, is transposed or not, that doesn't actually matter because you can always transpose like both points later. Someone asked if this is available later. Yeah, you can do the exclamation mark YouTube command to find my YouTube, where I upload things after like one day. Okay, so what we do here is we make a list of all of our points and their transposes. So we map or we add every original point, and then we also add with x and y switched, which is like if they're lying down. And then we also keep track later of the index of each thing. So like if we end up saying that a point from like the point 3 comma 4 is useful, then we want to know what the index in the original array was. And that's just for output purposes, because that's like the output format that they want. Whoa. I need to be more careful drinking water. All right. So then we sort the points, which sorts them primarily by x coordinate and then secondarily by y coordinate. Someone says cough harder. Yeah, I'm not sure too. Maybe I should drink a little more water. Okay, I think I feel better. All right, let's dive back into this. Um, so what we're doing here is we're gonna sweep through all the points, but we have to do a little bit of a trick here because we don't want to consider any point before the current point. We only want to consider points that have a smaller x coordinate instead of a smaller or equal x coordinate. So what we do here actually is we do this loop, which loops through a bunch of ranges of the array, where each range has all points having equal x coordinate. And this is like a pretty standard construct, which I can try to briefly explain. Basically, you find like the endpoint of the current block by whenever you're still having the same x coordinate, you increase the endpoint. And then you have the interval I through j, which contains all stuff with the same x coordinate. So what we're going to do here is we're going to say that our previous best point was, we're just going to put in this dummy point, which is -1. So it's left of any point, but it's much higher than any other point. Right, its y coordinate is 2e9, so it's never actually going to be useful. And it'll be replaced as soon as possible. So then what we do is we have two kind of separate things that we're doing here. First we're saying if our previous candidate to the left, if our previous candidate to the left is like possible to match with the current value, then we have this good map, which maps values of the bigger person to possible values of the smaller person, and we just add them to the good map. And then the other thing we do is we want to update our next best candidate by saying if we ever find something that's shorter than the previous best candidate, we want to use that instead. And then for our output, this is kind of gross looking, but basically for our output, we say if we couldn't find any good smaller rectangles for the current rectangle, then we print -1. And then if we could, we find the good rectangle, then we find its index from the original array. And then we have to add 1 just because here we're doing everything with 0 indexed because it's C++, and the problem statement is doing everything with 1 indexed because that's what they always do. So that's basically how this works. Yeah, the key idea here, which is actually a key idea for many geometry problems, is to sort by the x coordinate and then do like a line sweep. That's a really powerful technique, and I definitely recommend like familiarizing yourself with it. Cool. All right, and someone says waiting for C. So C I already discussed. I'm going through the problems in order. So you can go watch that on your own and, definitely hope that helps. Cool. All right, so New Year's puzzle. Someone asked how much time did it take me to solve? Yeah, so E actually took me quite a while, I think. Oh, these timestamps are kind of annoying. Yeah, so there's definitely a big jump, I think, from D to the rest. So the first four problems took me a couple minutes, and then I spent almost 20 minutes on just E. Um, mostly on debugging, so I think E could have gone a bit faster, but I initially didn't have a very clean solution to the problem of duplicate x coordinates, and then I wrote some messy solution to it, and then I ended up deleting all of that and then doing it the way that I currently did. And then F and G were kind of similar. I guess G actually took a little less time than F. And I think that in the round announcement, they had this weird clause, which was like E, F, and they said the problems had a weird difficulty order. And I think a lot of people agree with that. Like they found G easier than F, or like I actually found, I think, F easier than E, though it took me longer. I felt like it was, yeah, maybe not. I think I thought E, F, and G were pretty much similarly difficult as each other. Anyways, all right. So this F I thought was kind of a cool one. And at first I thought it was like super easy, and then I read the problem a little more carefully and I had to think a bit more. Um, so let's just go through what we might want to do, right? So I'm going to use a just a line like this to denote putting a domino across two tiles. So the kind of cool thing here is we can always just go from left to right and put the tiles in like almost greedily. So if we have two vertical spaces, we always want to fill them with a domino. If we have something like this, well, I guess I'll go through the easier case first. If we have something like this, then obviously we just want to do nothing. You can't put a domino there, and then you just keep going. And then if you have something like this, you have to put a domino like this. So then you kind of have to keep track of when you get to the next column. It's kind of as if there's an obstacle here. Cool. And then the reason that you always want to put vertical dominoes when you can is imagine any situation where you have two available spots and you want to put a horizontal domino. Then you also would need to put a horizontal domino like this. And if you're doing both of these, then you might as well just make both of them vertical. And that makes it a lot simpler. So you can actually just loop through the entire grid from left to right. And that would be O of n. And you can just fill in the whole grid. So at this point, I'm like, all right, we're done. This is pretty easy. But as some people are pointing out in the chat, this would get time limit exceeded because once I scrolled down and saw the input format, I saw, oh, they don't give you the grid, they just give you the locations in the grid, and the actual grid could be very large. So this would end up giving you TLE. So there's actually what I consider to be a pretty cool trick. So imagine your original grid is something like this. And then we have like this one filled in, and then we have like these two filled in, and then we have like this one filled in. So the cool thing that you could do is if you have a big gap with nothing in it, and like let's say this gap is of length, in this example, 1, 2, 3, 4, 5, then you can imagine like, well, you kind of know that if you have this big gap, you're always going to fill at least 4 of the things with just vertical. So you can actually remove them completely. So this grid that we've drawn here is also equivalent to this grid. So we got rid of the first gap, then we actually get rid of the second gap as well entirely. And then the next gap we reduce to size 1. And then that's actually it. That's like the whole grid. So the cool thing here is that now our new value of n is going to be like, I don't know, less than 3m maybe. Something like that. And once we've done this, we can just implement our original solution because now n is small enough that that will run in time. So that's pretty cool, right? So we had kind of a really straightforward solution, and then we just transformed our problem into the easier problem where we have that. And you do still have to be pretty careful when doing the implementation. There's a lot of cases where you could have an off by 1 or miss a case. So now I'll try to go through my implementation, and hopefully it is relatively clean. Whoops. Okay, so the first thing we do is we read the input, and because I want to compress things and sweep by someone asked, why are you saving one empty column? That's a great question. Let me see if I can think of a case where that matters. Okay. Yeah, so imagine like this case. It's not necessarily the case that here we would put a vertical domino because the solution here is actually like this. Um, so the reason that we need to only take out 2 by 2 blocks is because if you have a 2 by 2 block, then you can always remove it. And like you can kind of see that through this example where wait, actually, does that even make sense? Hmm. Yeah, okay. I think this is still right. Um, why didn't you see the second column then? Okay. So the idea here would be that if you have some solution that has a bunch of empty stuff, whatever you end up putting in that, if you have any 2 by 2 block, I think you should be able to shift the stuff in it by like adding 2 vertical dominoes. Oh, I guess here's the thing. You won't actually put 2 vertical dominoes, but if you have some pattern like this, you can remove this kind of like diagonal 2 by 2 block. Okay. So I think that explains that. But yeah, there's definitely a bit of intuition there, and you could make it more rigorous if you wanted. And I definitely encourage people to try to think about this on their own and think about, is there a way to make this solution even cleaner? All right, so I made sure to switch the row and column so that we kind of can sort things nicely by the horizontal coordinate. And then there might be other ways to do this transformation, but I did it the simplest way that I could think of, which was I kept track of the gaps between every pair, including the gap between 0 and like the first thing. And then I just reduced those gaps to either 0 or 1, depending on whether they were odd or even. And then um, I went through and reconstructed the original blocks, but compressed. Okay, so now that we're done with that, we basically, if you ignore like all of this, we have the original problem, but with the constraint that n is small. And then we can do our O of n algorithm. So the way that I implemented that is I thought of each column as like a binary number, and there's a lot of ways to do this, so it's not super important exactly what I did. But I thought of each column as like a binary number where like if the column is empty, it would be 0, 0. If the column has something in the top, it would be like 1, 0. And if it has something in the bottom, it would be 0, 1. And if it's full, it would be 1, 1. So I just implemented that here where I either or with a 1 or a 2. And then I did this trick at the end where at the very end, I just put in a vertical wall. And that makes sure that we don't have a domino that we fill in the whole grid, but then we have something hanging out of the end. So that would block that. And then what I did here is I just go through all the columns and I say that if the obstacle collides with like the extra stuff that we're sticking out, then we immediately know the answer is no. And then otherwise, you can do this via some casework, which is how I did it originally. I wrote like 20 lines of if statements. But basically, the idea here is that um, if you kind of just think about what the possibilities are, if you have an obstacle that has exactly one available spot and you've extended into that spot, then you're back to having nothing overhanging. And then if you have two available spots, then you end up overhanging on the other row, and stuff like that. So that's basically the solution to this problem. Um, by the way, definitely feel free to follow here and subscribe on YouTube and join my Discord. That would definitely be super cool. And if you can subscribe here, like with Twitch Prime or just subscribing normally, that would be awesome as well, but definitely not necessary. Okay, cool. So, right, let me hydrate. All right, so let's look at G, the last problem of the contest. So they drew some graph here. Basically, the idea for G, at least the way that I thought about it, is they have this kind of weird constraint where you have to find all the distances from the capital, and you can do that using a breadth first search. And then they say that you can only travel to something if it's further from the capital, except for once where you can someone asked, is there any way to do this without the approach that I did in F? So the answer is yes. I think that some other people did F via like a chessboard coloring where they looked at like they colored every square like red or blue depending on its parity, like a chess or checkerboard, and I think they had a cool solution using that. So definitely encourage you guys to think about that or read other people's code. All right, so yeah, so for G, you kind of have this weird constraint that you can only go to stuff that's further from the capital than you are, except for like occasionally. So the first thing I did is I tried to think about organizing my graph in a way that, like visually organizing my graph in a way that this makes sense. So here I have the capital, and then from the capital I can go to 2, or I can go to 3. And then this is distance 0, and then this is distance 1. And then from 2, I can go to 4, or I can go to 5. And then from 3, I can go to 6. And then there are actually some other edges. From 6, I can go back to 2. And from 5, I can go back to 1. But those are like special edges where you can only take those edges once. So, and so the way that I've drawn this, right, basically, I think this makes it a little easier to think about. Travel of the first type, which you can do as much as you want, is going downward, and travel of the second type is going upward or sideways. This example doesn't have any sideways, but that's fine for now, I think. So, first of all, so then let's find the answer for every node. So the first observation is the answer for every node is definitely going to be its distance or less, because you can just stay at that node and not do anything. Then the answer will also be the minimum of the answers for all the nodes that you can reach from your node using only the down edges. Because from your node, you can take as many down edges as you want and reach anything else, and then see what the answer is starting from there. And then the last little thing to keep in mind is that from something that's lower, you can go up exactly once. But from there, you can't go anywhere anymore. I guess you could go down from there again, but you wouldn't want to, because yeah. So basically, another way to think about this is your path will have a bunch of down edges and then one up edge, because after you take one up edge, you never want to go further away again, because that will never help you. Cool. So let's look at my code for that, which I think is fairly clear. All right, so we start by just reading the input into an adjacency list, and then take care that the edges are directed. So a lot of the time people will, usually you have undirected edges, so people will do this, but, just don't do that. Then here I wrote a simple breadth first search starting from the capital. So we find the distance to every node from the capital. And then what I did is I started from the bottom nodes and I went up and I computed the answer for each of those because the answer to a node only depends on the answers of its descendants. So this is a valid order to go through and kind of do like a DP. So here I'm just sorting so that the order of the nodes is sorted by the ones that are furthest away first. And then what I do is first I say, all right, so from my current node, I could just stay here. So the answer is at least as good as the distance to the current node. Then I go through all the nodes that I could reach. And if they are further away, if I'm going down with this edge, then I want to take the answer there and say that I could achieve that. And if we're going up, then I want to take the distance there and say that we could achieve that. Because I'm only doing one up edge, so I can't take the answer from there. If I did that, then that would be basically allowing multiple up edges, which is not allowed. And that's basically it. So that's how you solve G. Pretty short, clean implementation. Um, I don't have breadth first search pre-written, though maybe I should because it's so simple. I mean, it's pretty simple, but it would have saved me some typing, and it's always possible to make a bug. And someone's asking what's CK min. Basically CK min. Wait, where is it? It's basically saying A equals min of A comma B. The reason to use CK min is it's equivalent to writing this, but I think it's more clear and less error prone because you don't write the same thing twice. Basically, reducing code duplication is always a good thing. And then, cool. And then some people said they used matrix exponentiation for F, which is super cool. Um, I guess the matrix exponentiation solution is something like you do a DP of like whether it's possible or not, or you do a DP of how many ways there are to do it, maybe. Going from each prefix and then with like how much stuff is filled in. I guess I'll go back to F. Okay. And some people are saying let's look at geothermal's F. All right, so let's do that. Luckily geothermal is on my friends list. Show unofficial. Wow, geothermal did F real quick. And he got a wrong answer. So that's actually very efficient. Actually, luckily geothermal did so well I didn't need him to be on my friends list. I'm not even logged in. Okay. So, okay, cool. So I think this is like the chessboard coloring method that some other people were explaining. So yeah, I definitely want to look at this matrix solution as well. So I'll do that. Nice username. So I'll definitely look at the matrix solution next. But okay, I suspect if you do the matrix thing, you basically like you go through and like whenever you have a long gap, use the matrix exponentiation to skip it. And I think if you just think a little bit more from that, you can just realize that you can delete the long gap. And then you end up with the same solution that I had. But let's definitely look at it and see how that works out. All right, so let's look at geothermal's code. So what he's doing is, yeah, so he also switched them. What? if n is odd, then you can't do it. Is that true? Wait, how is this even right? Oh, I see. Okay. He switched. Okay, he also switched n and m relative to the problem statement. So that makes more sense. Yeah, so if there's an odd number of blocks, then it doesn't work. Okay, cool. Then we go through all the blocks and I see. So basically here he's trying to pair up every consecutive pair of obstacles once you sort this way and making sure that they're compatible with each other. Um, because I guess once you have one obstacle and you like work around it, it kind of creates like a hole in your tiling, and then the next obstacle has to fit into that hole. Um, so it would have to have the same like chessboard coloring. Um, and then there's this extra if statement of oh, maybe that's just saying that if you have like a vertical wall. Oh, I see. So whenever you have a vertical wall, you need all the stuff before that to be valid. So this is effectively checking this condition again, but every time you encounter a vertical wall. Um, cool. And then people are saying why if n. Okay, so this if n mod 2 is equivalent to saying if n mod 2 is not equal to 0, which is equivalent to saying if n is odd. So if you have an odd number of obstacles, you have an even number of total cells, which means you have an even number of non-blocked cells. Sorry, an odd number of non-blocked cells, as some people are explaining in the chat. And you can only fill cells in pairs, so that would definitely just not work. So yeah, this it's actually kind of funny. I think this if statement is like equivalent to this if statement in a way, but just a little bit like differently written because here we kind of have the I is even like already enforced, so we don't need to check that. Um, cool. So that's pretty neat. Um, Geothermal could have also deleted this if statement if he added like an artificial wall at the very end. So that's pretty cool. And then his code, I think, runs a lot faster as well. Um, because it doesn't have all this. Oh, I guess it's like the same because the code is pretty fast either way. It's mostly I/O. Okay. Now let's check out this matrix solution. um, oh, is the font a little small, by the way? Let me increase it. Um, okay. I strongly suspect that this matrix multiplication solution is exactly the same as what I did, but where these ones are encoding like valid transitions. Um, and then you're using matrix exponentiation instead of um, just modding this thing. Yeah, actually, so I think if you took this matrix and you like squared it or something, you would get the identity probably, or maybe not. Hmm. Okay, cool. Yeah, so the author said that they used matrix exponentiation to skip big gaps. Yeah, I'm kind of curious what the powers of this matrix are. I can't really do matrix powers in my head that well. Um, but let's see. So t equals 1. So this is like the original t, so then t squared would be like, well, this would be 2. And then the next things would be like 0. Hmm. Yeah, I guess I won't actually oh, it's multiplication mod 2. Wait, what? Where is that? Oh, I guess is that what this is? Wait, this isn't multiplication mod 2, is it? It's like this is like multiplication where you have like or as plus. Okay. I guess maybe let's just run this. Oh. Oh, and then you multiply by this column vector. Okay, anyway, I strongly suspect this is like some kind of periodic thing that basically checks if it's um like odd or even. Nice. Someone said demoralizer has become remoralizer. Um, cool. All right. So I guess that kind of wraps up this contest. Let's see if anyone's getting hacked. Wow, it looks like there's a ton of successful hacks. Um, yeah, this is a bad day for, yeah, all these LGMs are getting hacked. Pretty exciting. And then it's actually crazy. All these LGMs managed to compete officially instead of unofficially. Like this candidate master competed unofficially, but then a ton of these people getting hacked managed to compete officially. I guess they must have hacked CF or something. Um, all right, yeah, I guess let's look at some of these successful hacks and see what the bugs were. I'm kind of curious. I don't know. Seems right. Someone said, when will this be uploaded to YouTube? So I upload to YouTube typically within a day, and you can subscribe to my YouTube here and join my Discord here. Yeah, it might be an n squared sort for some of these hacks, but I kind of doubt that also because it seems like it's hard to force an n squared sort when your only values are 1 and 2. Um, but maybe it's possible. All right, cool. So this seems like a good time to wrap up the stream. Pretty good contest overall. Fun problems. I particularly liked G. I thought it was kind of cool because it seemed super complex at first and then ended up being pretty simple. Um, and yeah, E and F were cool as well. E was a nice standard line sweep. D was a cool problem where it was like a game where you have to transform the game. And then A, B, and C were relatively standard. And then F was just kind of weird. um, but yeah. Cool. So yeah, thanks so much everyone for joining. Thanks for the kind words, and definitely be sure to follow me on Twitch, subscribe to me on YouTube, and join my Discord. Um, and yeah, some people are saying F was cool because it had a lot of different. Well, they didn't say why, but I think F was cool because it had a lot of different solutions, which I think was kind of neat. Like I think everybody did G the exact same way, even though it was an elegant problem. Maybe because it was an elegant problem. But yeah, thanks so much, everyone, and see you guys next time.